Hello everybody, this is Jinqing Liang. Here I will continue to talk about my capstone project, brain aneurysm detection using 3D cerebral angiography dataset. I will focus on the three parts in the deep learning pipeline. First, I will talk about the dataset and its processing. In this part, I will focus on the data characterization, data sampling, and the data augmentation. Second, I will introduce the method used for 3D network training, which including dealing with unbalanced data by oversampling and hyperparameter tuning. Finally, I will show the result of the model performance. The histogram at the left shows the distribution of number of dots among the samples. The minimal number of dots in a sample can be as small as 9 or as large as almost 4,000. In the vessel category, the normal blood vessel has about 1,700 samples, while the aneurysm category only has 215 samples. The aneurysm samples, however, have its minimal number of dots at 500, and then use the 500 as a cutting point to select the samples. The samples with less than 500 dots will not be used in the project. As shown in the previous slides, the number of dots in the point cloud of each sample are quite different. For 2D image, we can shrink or enlarge the images to keep the image size consistent and fit the requirements of neural network. For the 3D image dataset, we can use random sampling and get part of the dots from a sample. Here we randomly select 500 dots for each sample. In 2D image classification, we can conduct image augmentation by rotating the image by a variety of degrees. Similarly, to make the model robust for 3D objects with different angles, the training sample will rotate along the z-axis. Every time when a sample is retrieved from the training dataset, the 3D object will be rotated in a random degree. As we usually do for 2D image augmentation by adding noises, random numbers in a range of 0 to 0.02 are added to the x, y, z coordinates of the dots to shift a little bit of their positions in 3D spaces. As mentioned before, the two classes of the datasets, vessel and aneurysm, are largely unbalanced. The vessel class that is normal blood vessel has about 1,500 samples, while the aneurysm class only has about 200 samples. If we train the neural network model using the unbalanced data, the model will be biased and show favorable prediction towards the normal blood vessels. To make the sample in the two classes has the equal size, or the sample will register in a data frame, the entries of the aneurysm sample will oversampled to match the number of vessel samples. Then, we will have multiple replicates of each aneurysm samples in the data frame. The same number of vessel and the aneurysm sample will be included in each batch of training datasets. Our data augmentation method will make sure the method will not see the exact same samples. I conducted several rounds of hyperparameter tuning, including selecting a proper initial learning rate and a number of epochs. Eventually, I used a learning rate of 0.001 and the epoch number of 160 for model training. As shown in the images, the training loss continued to reduce to below 0.1 at around the epoch of 150. Similarly, the validation accuracy reached its highest point around 0.97 at epochs from 130 to 150 epochs. The PyTorch model with the best validation accuracy was used for testing. The trained model showed a high performance for validation dataset with the AUC equal to 0.99. This model also shows similar performance for vessel and aneurysm samples. Then I checked the model performance on testing dataset. The model showed a pretty good performance on vessel samples. However, the model performance on aneurysm sample is not ideal. The overall accuracy was 0.88. The trained model has an AUC value equal to 0.9 on testing dataset. To summarize, in this project, I detected the existence of aneurysm in brain. by training 3D PointNet neural network using 3D point cloud dataset. The normal vessel and aneurysm dataset were largely unbalanced, so I upsampled the aneurysm dataset by using data augmentation techniques like rotation and adding noisy dot. Then the model was trained and its hyperparameters were tuned using validation dataset. Finally, I tested the model performance using the preserved testing dataset. The model has an AUC of 0.9. The work in the future I will focus on increasing the prediction accuracy on aneurysm samples. I noticed that when people check the 3D images, they usually rotate the image to find the aneurysm. I will implement this mechanism in aneurysm detection for the trained models. Here are some resources for references. Thank you. If you have any questions, please email me, or if you need more details on my project, please check my GitHub.